So ammonia making, or ammonia industry, basically we need to look at based on the reversible reaction rules and Le Chatelier principle. I said ammonia is extremely important because ammonia is needed for all sort of fertilizers, like famous fertilizers, ammonium nitrate, because fertilizers are the one that provide basic elements like nitrogen, phosphorus and potassium, along with zinc and iron and calcium. These are traces, but you need large amount of nitrogen and phosphorus and potassium. Nitrogen especially because that is needed for protein building, and ammonia is needed to make all sort of fertilizers like ammonium nitrate, ammonium phosphate, ammonium carbonyl, urea. Okay, most famous common fertilizer that contain large amount of nitrogen. 35% plus nitrogen is being provided by urea, and you need ammonia for making some other things like nylon. You need ammonia for making nitric acid, and nitric acid can be later used to make explosives, TNT and explosives, fireworks, so many other uses. But ammonium production was, I said earlier on in the intro, was very slow, dead slow. Reason, nitrogen and hydrogen were reacting to produce ammonia, but the reaction was reversed and stuck to the state of dynamic equilibrium at a point that it was only 15% this side and 85% this side, and it was stuck to the state of dynamic equilibrium. But improvements based on Le Chatelier principle has turned the dynamic equilibrium, pushed the dynamic equilibrium, favored the dynamic equilibrium to the product side up to such an extent the yield of ammonia has gone 90% plus, and the process is not that expensive anymore. Nitrogen needed for this process, large amount of nitrogen is present in the air, 78%. Okay, and that nitrogen is fixed by atmospheric situations like lightning strikes and turned to nitrates, but the process is rare and slow. Or that nitrogen is also fixed by bacteria living in the plants, the leguminous plants, in their nodules, in the soil those bacteria live, and they also fix nitrogen. Fix mean turn into ammonium compounds or nitrates, so the plants can sip in, because plants cannot basically incorporate free nitrogen. Nitrogen, very stable molecule, and triple bond N need a very high energy to break. So nitrogen as such goes in our bodies and come out. Same for the plants. We cannot fix it, otherwise we need to eat no food, possibly. But plants cannot sip free nitrogen. Nitrogen has to turn into nitrates or ammonium compounds, and this is done, this process is nitrogen fixation, done by nature lightning, done by leguminous plants, bacteria, but processes are very slow. These days, increased population, we need artificial fixed nitrogen in the form of ammonium compounds, and that was done by Haber process. Nitrogen is being obtained from the air because it has largest amount, but not from the air, by fractional distillation of what? Liquid air. That is the process. Air is first removed of carbon dioxide and water, so the compressor never get blocked, and then air is cooled, and cooled, liquefied, minus 200 and beyond, and when it is heated, nitrogen start oozing out at minus 196 and is collected in the large amount and supplied all around the world for ammonia industries. Okay, that liquid nitrogen is also used as a coolant, okay, as a refrigerant. And hydrogen, again another rare thing, is obtained by cracking of the hydrocarbons. Large amount of hydrocarbons, fossil fuels, their cracking yield one byproduct, that is hydrogen. And also by the reaction of steam in the natural gas, hydrogen is produced. So these nitrogen and hydrogen both react and produce ammonia, but reaction is reversible. You can notice this thing, since these are gases, so in order to improve the rate of reaction in terms of kinetic particle theory, gases has to press, so the particles come closer, and pressure in terms of kinetic particle theory will improve rate of forward reaction as well as rate of backward reaction. But when we need to improve the yield in terms of dynamic equilibrium, then the yield can't be improved by any other factor rather than the Le Chatelier rule, and the rule says if you create a change in the reaction which is stuck to the state of dynamic equilibrium, reaction will counter strike and oppose the change. Now in this case you can find out there are 4 moles on the reactant side and 2 moles on the product side. When pressure has to come into practice, then we count only what? Moles. Moles of gases are 4, reactants are 4 and products are 2. So if we increase pressure, reaction will oppose the change, and by opposing the change it will move to the side with less moles. You increase pressure, reaction will say okay, I'll decrease it, and it can only decrease the pressure, oppose the change by moving to the side with less moles. Easy to remember. Increase pressure will shift the dynamic equilibrium to the side with less moles. In this case it is product side. That is the reason you will notice that any graphical representation will show that increasing the pressure will increase the yield, and almost at 1000 atm, which is a huge pressure, ammonia yield is almost 100%. But increasing the pressure also increases the cost. So depending on the situation and the country and how much you can afford, basically the industry, the pressure is adjusted, but normally it lies 200 and beyond. The best may be 200 atms, too much. Okay, but a very high pressure may increase the yield. Definitely will increase the yield, but also it increases the cost of the reaction. So it is adjusted in between 200 and 1000 atm. High pressure will shift to the side with less moles. Luckily this is the product side, the less moles, and that's why any high pressure value you will shift the dynamic equilibrium to the product side. So pressure is kept at high. Then what the temperature is needed. Remember, when we want to discuss the effect of temperature, then you need to look at this value, the delta H value, and delta H in this case is negative. It is 92 kilojoules per mole. Even this value is not mentioned, only delta H negative mean it is exothermic in the forward side. When it is exothermic in the forward side, it means the backward is what? Endo side. So we need to be careful again. Le Chatelier said increase the temperature, reaction will move to the side which oppose the change, and of course it will oppose the change by moving to the side which is endothermic. So if you will increase temperature, reaction will move to the reactant side, because reactant side is endothermic, forward side is exothermic. So increase the pressure, increase the temperature, reaction will move to the endothermic side. It means that it will be counterproductive. The pressure is kept high and temperature is reversing it back. So we need to adjust, and we'll look at the delta H value, it's negative. If a very high temperature is supplied, reaction will move to the endothermic side, but if a low temperature is supplied, reaction will move to the exothermic side. If a low temperature is, because reaction will oppose the change. So high temperature will favor the endo side, that is reverse, that is left side. Low temperature is needed in this case to improve the yield, but a very low temperature will decrease the rate of reaction, because temperature again, kinetic energy, it provides the kinetic energy, it improves the collision frequency, it is needed for activation energy. So a very low temperature may improve the yield of the product in this case, but rate will be less. So there is a reason we compromise it. A yield is compromised a bit, but rate is improved. So 350 to 450 degrees Celsius is considered to be the best optimum condition for the Haber process, where yield is also appreciable and rate is also appreciable. So that is the best operating condition for temperature 350 to 450. Okay, somebody may ask why high temperature. He'll say it's not high, it's compromise, because a very high mean shifting it to the product reactant side. So it is kept between 350 to 450. The word compromise is used because it actually adjusts the rate as well as yield. Yield may be compromised a bit. And pressure of 200 to 1000 atm, and iron as a catalyst. Fe, transition element, iron is a catalyst. Transition elements are best catalyst. Iron is a cheaper option. Beds, huge beds of the iron catalyst, where gases are adsorbed on the surface and activation energy is lowered. Iron oxide is not the catalyst, it's only the promoter that adjusts in the collisions. Okay, so these are the best conditions, but same time nitrogen and hydrogen are constantly being injected into the system. So the reactants are always kept at a higher situation, and product ammonia is removed from the system. That was a very smart option used by the Haber. He keep on removing ammonia by applying a condenser, and the condenser has cooled it down to minus 39 degrees Celsius. So at minus 39 degrees Celsius, ammonia turned to liquid ammonia. It is leached out of the system. So reactants are removed constantly and products are injected constantly. So the dynamic equilibrium is always shifted to the right side. Because if you are not removing the product and increasing the reactant, it means reaction is stuck to the state of dynamic equilibrium and there will be no apparent change in the yield. The yield may be only 15% even applying these conditions. You need to be smart. Remove ammonia. Dynamic equilibrium is disturbed. And the reactants will react to turn into product according to the Le Chatelier rule. So to attain the dynamic equilibrium, again, heat condenser basically, heat exchanger was added into the system. Ammonia is liquefied to minus 39, constantly being leached out, and unreacted nitrogen and hydrogen is sucked back and added into the system, and also fresh is added into the system. So keep reactants at a higher situation, remove products, dynamic equilibrium is always shifted to the right side and your yield will be maximizing in this situation. Always this is done with reversible reaction, that products are being leached out and reactants are constantly being added. Also nitrogen, expensive gas, can't be released into the air, hydrogen catches fire. This also cannot be released into the air, okay? So constantly sucked back, unreacted, passed over the heated catalyst, and ammonia is being removed by the heat condenser. By applying these smart techniques, the Le Chatelier rule, Haber was able to achieve a 98% yield and he got a Nobel Prize for this, all we know. And because ammonia mean the prosperity of a nation, because ammonia mean all the fertilizers and the nylon industries and the nitric acid. This is how, using reversible principle rules, Le Chatelier principle, Haber was able to tackle the situation. Smart chemistry, reactants are forced to turn into product, but products is removed constantly and not allowed to react back, reverse back, and that is how basically the reversible reaction is tackled in ammonia industry.
ये ली शैटलियर और हार्बर अलग अलग लोग हैं।
हाँ,
अच्छा तो ली शैटलियर को क्यों नहीं मिला?